So I didn't know this was off. Processing. Power and efficiency. Okay. Got that? Yeah. Some of these words you might know. So let's have a look. It might not be too hard at this lesson. Okay. So this is my example to get us thinking. Imagine you carry 1 kilogram up a hill. Now imagine 1,000 ants each carry 1 gram up the hill with you. So one ant goes up with 1 gram, another ant goes up with another gram. One by one. Between the two of you, who has done more work? So at the top, there's 1 kilogram and 1,000 grams. You carried the 1 kilogram up, and the ants carried the 1,000 grams up one by one. So you see your 1 kilogram and the ants 1 kilogram. Who did more work? What do you think? Seems like it, doesn't it? But actually no. The amount of work is the same for both, yeah. Well, why is it the same? Well, the formula for potential energy is mgh. Is the h the same? Yeah. Is the m the same? Yeah, so the work is the same. But something feels wrong because we kind of feel like, well, there's something different between the two pictures. And the difference is that the time for the ants to do this work is more than time for you to do the work. So it's not only work that's important, but how quickly you can do the work. The time for the work. So this gives us the idea of power. So power is, the work over time. Work per time. It's the work done per time, and as a formula, it's work over time. So what would be the unit using this formula? Joules per second, yeah. But we actually use a different unit, which is called a watt. But 1 watt is simply 1 joule per 1 second anyway. So, if you can write both these definitions down, please. What? 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 You wrote this definition down? Yeah. Do you mind opening the window, please? Oh, come on. Be strong. You just one window's enough. Yeah. Yeah, no, keep an eye, you're right. There, yeah. No, nice fresh air. You have this? You have this? Yeah. By the way, the unit is named after the person, James Watt. But it means you could actually make a sentence like this. Oh no, there's no H in this name, sorry. Yeah. Yeah. Can you see? Because this is the question, this is the person, because of the S, and this is the thing. Yeah. So you can make a sentence with the same word 3 times. You can look this up in English. It's the longest sentences, making sentences with just one word. So, yeah, I can think of a sentence with the same word 6 times. No, a real sentence. Have you not seen this before? No? I'll show you. It's a sentence with 5 words that are all the same. But each word has a different meaning. So you can figure it out. Look here. This must be a person. This is a person named Badger. And this one here, person. So this one here is a thing. Yeah, what? Does anyone know what it is? Yeah, what is it? It's an animal. It's an animal, yeah. So this one here is a verb. And this verb actually means to annoy. To annoy someone. So, badgers, badger, annoys, badgers, badger. Not seen this one before. Okay. You can remember that for EAP. It's the longest sentence I can think of that has the same word used 5 times. There are other examples which are longer. But there's something like this in Chinese, like a poem, where it's the same word repeated. You know this poem? Something about dragons, crying dragons, eating dragons, stone dragons. I don't remember. You don't know what I'm talking about?
No, I have no idea.
No idea? No problem. Okay, continuing. Right, so when you convert electrical energy into light energy, you've not used up any energy. You've just converted it. So like for example, the electrical here becomes light. You don't make the energy, you just change the electrical here into light. You've converted it. But the electrical energy was not only converted into light, which is what you want, but it was also converted into heat, which you don't want. So, if you have a 100 watt bulb, that means it's using 100 joules per second. So it's taking 100 joules per second, converting it. How much do you think of that 100 joules is actually light? And how much of the 100 joules per second is heat? So how much is what you want, and how much is what you don't want? So what do you think the numbers might be? 100 joules a second, how much gets turned into light, and how much gets turned into heat? As for a normal light bulb, an old light bulb. Yeah, so what do you think the numbers might be? If you were to guess, 100 joules, how much do you think might be light? You're going 60 light, 40 heat. Good, okay. What about over here? What do you think? 65, okay, so about the same then. What do you think? Of the 100 joules, how much is light and how much do you think is wasted as heat? 80 for light, 20 for heat. Good, okay.
Maximum 40.
You say maximum 40 for what?
Right.
Light. 40. Okay, so you're the lowest so far, okay?
90 and 10.
Oh, okay, so 90 for light and 10 for heat. Okay, so you're the highest so far. Anyone else? 90 for heat and 10 for light, so the opposite of hers. And over here, what do you think? No idea? No? Ah, come on in. It is, in fact, for light, 1. 1 joule for light, 99 for heat. Yes. Close, but I think Bruce said 10 joules for light. There's only 1 joule for light. Now this is for the old light bulbs, you know, the ones that look like what you see in the cartoons. You know, these old light bulbs, you put in 100 watts and out comes 1 watt of light, but then 99 watts of heat. Now, the newer light bulbs, I have them at home, they're the LED lights. They look like normal lights, but actually inside of them there's lots of LEDs. These are actually a lot better. They use, I think the ones I had, they use 4 watts. And I would guess, although I'm not sure, of the 4 watts, I'd say most of it's actually light. I'd say it's maybe 3 watts light, 1 watt maybe heat. So that's a big difference. The total is much less. And instead of being 1% useful, it's 75% useful. Something like this. Yeah? So this gives us our next idea, which is what we call efficiency. It's how much useful work we get done. Now maybe some people can figure out the formula or might even know the formula. What is efficiency? It's a percentage. How would you calculate it? If you think about power that goes in and power that you want that comes out, how might you make it a percentage? What do you think? The ratio, yeah. Which divided by which?
In.
Yeah.
Out.
Yes. Yes. In, out, multiply 100.
Yeah.
Yeah. So the formula is, I would say it's out in rather than in out, but it's the same thing. Output over input times 100%. That's the efficiency. If you want to write it, you can actually write it like this if you like. Energy out over energy in times 100. And if you want to be more specific, you could say useful energy out over total energy in. You don't have to. Okay, you got that? Don't worry. I'll wait for you. Now tell me, what would happen if I divide the top and the bottom by time? So energy divided by time and energy divided by time. What would I get? Yeah, but what is energy or work divided by time? Power, yeah. So I could also write the formula like this. Power out over power in. Gives me the same answer. Now, ideally you would want efficiency to be 100%. But in fact, this is impossible because of heat loss. It's always less than 100%. So can you write this version down? And also please note that efficiency in real life is always less than 100%. And I have bad news to tell you. It's actually impossible to make something 100% efficient. It's an impossibility.
Our body is very nice.
I don't know. I wouldn't say so.
40%.
40% is what it is for humans.
Yeah.
A car is about, it depends on the car, I guess, can be anywhere between 25 and 35 maybe. Does anybody know what might be the most efficient thing in their home? Think about all the things in your home. Which do you think is the most efficient? So the thing that's the least efficient is the light bulb, because it makes so much heat and so little energy is actually used for light. Although the new light bulbs are better. But the opposite, what is the thing in your home that you think is most efficient?
Heater.
Very good, yeah, a heater. Electric heater. Because the heat loss is actually what it's supposed to do. It's supposed to give out heat. But remember I said nothing is 100% efficient, so even the electric heater, whose job it is to make heat, there is some wasted energy, something which is not useful. What might that be for the heater? Sound and light, yeah.
Microwave.
Yeah, because if you look inside the heater, you'll see it glowing. You don't actually care about the light coming out of the heater when the heating element glows. You only want the heat to come out. You don't want any light to come out, and you don't want any sound to come out as well, because you only care about the heat coming out. Yes, and the microwave is actually pretty efficient as well, although some heat is lost out the back of it.
What about the toaster?
I'd say a toaster is actually pretty bad, because I can picture lots of heat floating out the top of it as it's toasting your bread. Yeah, but you would like the heat to stay in it, because if you could keep the heat in it, then you could toast the bread quicker. But it's leaking out the top. Toaster is pretty bad. And what else? Phone chargers are okay. New TVs are okay, actually. A new TV, yeah, they're okay. I know I won't support any particular brand. I think they make some TVs in Korea, don't they? Yeah, I think there's some production of TVs there. Yes. And computers and laptops are not great. They're pretty low. Yeah, laptops make a lot of heat and noise. Computers are kind of the same. Lots of heat being made. In fact, they make so much heat, as you know, they need a fan to cool them down. This is really wasted energy. You know, a computer might be 50 watts, and less than 1 watt is useful. I don't even think it's maybe 1 watt. It's fairly bad, because it makes a lot of heat, which you really don't want. In fact, not only do you don't want it, but it could actually damage the computer if it gets too hot. It's actually worse than that. Okay, you got this formula down? Yeah. Right. Here is a simple question which I think you can do. A boy lifts a 2-kilogram physics book off the ground, a height of 1.1 meter. It takes him 2 seconds to do this. What is the power in his arms? Okay, so the power is the work divided by the time. What work is he doing here? Potential energy. He's given the book potential energy. So the formula here would be work over time, which would be mgh over t. Can you calculate this, please? I think the answer will be about 10 joules, 10 watts. But can you calculate for this? 10.8. Okay. Yeah, it's 2 times 9.81 times 1.1 over 2. So the 2's cancel and it's 9.81 times 1.1. So what did you say that was? 10.8 watts, yeah. Now, he got this energy from his breakfast. However, half the energy is wasted as heat. What is his power now? Yeah, the efficiency is 50%. The output is still the same. He's still doing the same job, but the input from his arms is different. The input and the output aren't the same. If he's only 50% efficient, does his arms need to be more powerful or less powerful? More powerful, because half of his energy is wasted. So his arms need to be twice as strong. Now think about your toaster, okay? If the toaster is only 50% efficient, if 50% of the heat is lost, then you need the heating element to be twice as powerful, because you're going to lose half of it. So the output is still the same. The output is still 10.8. The input we don't know, but we know the ratio is 50%. So can you calculate, please, what the power input is now? 21.6 watts. Yeah. Is that okay, or are you confused? I can't tell. Or hungry? Which?
Confused.
Confused, okay.
Hungry.
What's confusing you? And hungry. No, you're not confused, you're just hungry. Yeah.
Okay.
Go on, what is your question? So what's happening here? Whoops. In the first picture, the input equals the output. The work he does equals the power in his arms. Nothing is wasted. Yeah. But suppose he wants to use 10.8 joules of energy to lift the book up. Well, if he's 50% efficient, he can't. Because some of that energy is going to make heat. As he lifts the book, he gets hot. He doesn't want to get hot, he just wants to lift the book. So, the power out over the power in times 100 equals 50%. Now this is the same job is being done. It's the input that must be different. In fact, by this formula, it must be twice as big. Yeah. It's because the energy is wasted as heat. It means more input energy is needed. Yeah. He needs more energy from his stomach, because he's going to waste half of it, making sounds as he lifts the book and things like this. Yeah. Is that okay? I hope so. Right. A 1,200 kilogram car starts at rest and reaches a speed of 100 kilometers an hour, and it takes it 10 seconds to do this. If the car was 100% efficient, which it's not, but if we say it is, then what is the power of the engine? So the power is the work over the time. What's the time? 10. What's the work? Yeah, given the car kinetic energy is the work done. Now be careful, you're going to have to change a unit here. The speed should be in meters per second. Right, calculate part A, please. Just part A. I'll calculate it here. Oh, you missed this lesson. This is actually our first lesson. Yeah. You need to watch this video.
I watched the video
Good. I will show you how to do it in a moment. Yeah. Can I have a look here? So, the power equals the work over the time, and the work done is given the car kinetic energy. A half, 1200 over 10, and then this is the V squared. What the heck? Come on. Hello? There we go. 100 kilometers per hour. Now, how big is a kilo? 1,000. So that's 100 times 1,000. And how big is an hour in seconds? 3,600. Right, so that's cancels a 0. and a half of 120 is 6, and cancel 2 zeros here, so it's 1000 over 36 squared times 60. What's that, please? Do I have my calculator? Oh, I have it. Woohoo! Pretty big number, I think. 46,000. 46.3 kilowatts. That's actually pretty low for a car. I think this. Well, no, it's actually not that low, but it would be something along the lines of a Nissan Micra or Toyota Yaris, perhaps, would be a power rating like this. Although that's, of course, if the car was 100% efficient, which it's not. It's only 40% efficient, which is still actually pretty good, 40% efficient. So does that mean the engine needs to be more powerful or less powerful to do the same work, to get to the same speed in the same time? It needs to be more powerful because it's losing energy in the form of what? What form does a car mostly lose energy in? Heat. Yeah, the engine gets quite hot. So, power out over power in times 100% should equal 40%. So this means the power in, which is from the engine, if I do 40 over 100, no, sorry, the other way around, if I rearrange it, 100 over 40 times power out. So what I did was I just swapped the power in with the 40, just did a swap around. So now I have this formula. So if I just multiply my answer here by 100 over 40, and let's just make it kilo again. Yeah, okay, so 116 in part B, it's 116 kilowatts. Now the car is no longer a Nissan Micra. I don't know if it's going to be a Jeep. What would be a car? What would be a car with a 2-liter engine?
2 liter.
2 liters, yeah.
Big car.
Yeah, like what?
BMW 7.
Okay, BMW 7 then. It's more like this then.
Or Rolls Royce.
A Rolls Royce 2. Yes, I suppose so. Yes, yeah.
Or Hummer.
I think a Hummer might even be more than this. I think so. Hummers are terribly inefficient. Terribly inefficient. I think a Hummer's efficiency is like 10%. It's horrible. Because it's just too big.
Yeah.
It's just too big.
Nice.
That's not nice. Anyways, we don't drive big cars here. We'd have to talk to our students from the Middle East now. It's just everybody drives a Hummer over there, no? Or, do you even have hatchback cars? Ever seen a Nissan Micra before? You have? Yes, they have them. It's the car Lorraine drives. It's the small car. Now you see, I'm sure you've seen Nissan Micras before. No, what's a small car in Malaysia then?
I don't think. Yeah.
We have a small car.
Cube. Like cube car.
Cube car, yes. Mini, yeah. Yeah.
I don't see a lot of sedan cars here.
No, hatchbacks are very popular. Do you know hatchback? It's the car that doesn't have a boot at the back. It's just a straight, like a Yaris, yeah, or a Micra or something, yeah. These are quite popular here.
Why? What's the reason? Why is it popular here?
Cheaper? Tax is cheaper. Car tax. Petrol is cheaper, and insurance is cheaper.
Because cheaper.
Everything is cheaper about it. Yeah, everything. The tax, the insurance, everything is cheaper. Yeah.
How do you get B again?
Huh? B? Oh yeah, this one here. I have to rearrange it, no? This answer multiply 100 over 40 is not this? The 46.3. multiplied by 100 over 40. You don't get this? Did I type it in wrong? Is this right? He wants to know how I got the 116. Oh! If it's 40% efficient, what's the power?
Kilos.
Yeah, kilowatts, yeah.
Like 1157.
Yeah, so I rounded it off.
Why is it 100 over 30?
Because I said in part B it's 40% efficient. Not happy with that?
It shouldn't be 40 over 100.
Well, no, what I said was power out, which we do know, over power in, which we don't know, times 100 equals 40. So power in equals power out times 100 over 40. I basically just swapped these two in the formula, just cross multiply. This is the thing we want, and this is the thing we know.
Compare to the question.
Okay, have a read and have a think.
The small cars in Malaysia are the national company cars.
Yeah, so I've probably not heard of them then, yeah. They export the Malaysian cars to China?
No, they sold 49.1% to a Chinese company.
Oh, the ownership of it, okay.
No money.
Malaysia's running out of money, isn't it? Yes.
So when the first one you calculate is useful output energy?
For A, yeah. And that's still the same useful output energy in B, because you still want the car to do the same speed in the same time. But because there's wasted energy, the engine needs to be more powerful.
Have we calculated the input energy?
For part A,
Yeah.
we did. The input and the output are the same in part A because they're 100% efficient. It's only in part B where the input and the output are different because it's 40% efficient.
So the input is more, is the same?
The input is different, the output is the same. Because the car is doing the same job. You want it to do 100 kilometers per hour in 10 seconds. But if it's wasted energy, it needs to have a more powerful engine. You don't seem happy. Tell me what's confusing you so I can help. No?
Shouldn't the smaller number be on top?
No? Well, it is on top. So if I write it out like this, maybe this would help you. This is X. This is 46300 times 100 equals 40.
Oh.
So B is just to find the weight.
Okay.
Yeah?
Right.
Is it okay? Yeah, I don't know. I don't know what else I can say. Shall I continue? Maybe you need to have a think about this. Drink some coffee, meditate, light a candle. Okay. A pump in a basement pumps oil from a tank at 6 kilograms per second into a boiler which is 10.19 meters above the pump and tank. So this is a very big boiler. It pumps 6 kilograms per second, which is 10 meters above the pump and the tank. The oil enters the boiler at 2 meters per second and the pump is 75% efficient. What is the power? So let me just draw what's happening here. You have a basement, and in the basement they store a large amount of oil. And then up at a higher level is the boiler. And of course you need to get the oil from the basement up to the boiler. And the pump can do this at a rate of 6 kilograms per second. So every second it can send 6 kilograms up to the boiler. And the oil enters the boiler at 2 meters per second. So when it goes in, flows into the boiler, it's going in at 2 meters per second. That's how quickly it's going into the boiler. Okay. And I also tell you that the pump is this pump here that's doing all the work. The pump is 75% efficient. Okay, I think I'd like to do this one together. It's a little bit tricky. So, the easiest way to do this first is just look at it per second. So in 1 second, what has the pump done? It's taken 6 kilograms out from here and it's pushing it up to here. So in 1 second, the mass is 1 kilogram. Let me just write that in. Sorry, not 1 kilogram, 6 kilograms. Now, what is the pump doing? Like, what is the work that the pump is doing? You can actually think about it 2 ways. So I wonder what way you think about it. What work is the pump doing?
Pumping.
Okay, 3 ways then. So what is pumping though? What energy, what work is it doing? Like what form? Kinetic is one way to think about it. You can think about the pump giving the oil a kinetic energy so it can push it along the pipe. That is true. So the work done is kinetic. Or there's another way to think about it. Potential, yeah. Because it gives this kinetic energy, but the kinetic energy is going to change into potential up the top. So you have a choice. No. I will not choose this because I actually don't know how fast the oil is here. I don't know how fast it pushes the oil. I only know what happens at the end. So if you look here, there's an energy here and an energy here. The energy at the top is actually potential plus kinetic, and the energy at the bottom is just kinetic at ground level. But we know from conservation of energy that these must be the same. Which is easier to calculate, E1 or E2? E2, because for potential energy we need to know the height. Do we know the height? Oh, I'm sorry, I didn't draw it. We do, 10.19. And for kinetic, we need to know the mass and the speed. Do we know the mass and the speed? Yeah. And we said we're looking over a per second basis. We look at what happens in 1 second. It takes 6 kilograms and pushes it. So the time is 1 second. The pump is doing this work over 1 second. Now don't be confused. Many seconds have to pass for it to get up here. But at that point, the pump no longer is caring about the 6 kilograms because it's left. It's already done the work to it. So it's not actually important how long it takes to get up here. So the useful output is mgh plus a half mv squared over 1. It's a 1 second time we're looking at. Right, so let's see what this is. mgh plus 12, isn't it? That's 611.78 watts. Now, of course, that's not the real answer because we have to remember it's 75% efficient. What energy is being wasted here with the pump, if you think about a pump?
Friction?
A lot of sound and a lot of heat, but a lot of sound. You know.
Sound.
Oh yeah, pumps are loud.
Yeah.
They're very loud. So, power out over power in times 100 equals 75. So the input power, let me see, that would be 100 over 75 times 611.78, which is, yeah. $816 watts. 816 watt pump. Now, if you're looking at a pump and it tells you how powerful it is, will it tell you the input or the output? What do you think? Think about it. You want to know how powerful your pump is, and you see on the pump it says 1,000 watts. Is that 1,000 input or 1,000 output? Oh, good. We have two answers. Great. Great. You look at a pump, and on the pump you can see it says this is a 1,000 watt pump. Is that 1,000 watts, do you think, for the input power or the output power? Okay, we have one answer.
Okay, we heard that.
You're thinking deeply about it. Good. How strongly do you feel about this? Okay. Any other answers?
Output power.
Okay, good. Any other opinions? No. It is the input.
Why?
I'm afraid to tell you. Yeah, because you need to know what the input power is because you're going to connect it to this.
Should be come in that what?
Yeah, it needs to say the input power because you need to know how much electrical energy to give it. But the input power is not useful because if it was only 10% efficient, you know, if this was 816 watts and only 10% efficient, you'd think you've got a powerful pump, but instead you've got a pump that's only doing 81 watts of useful work. So unfortunately, I feel like most appliances, they should say the power on it and how efficient it is. Now in Europe, it's now I think legally required that for some things it has to say how efficient it is. So washing machine, dishwasher, fridge, cooker, all these things, they have to say the input power and also the efficiency. But what's annoying is they have to give the efficiency as a grade, like A, B, C, D, which I want to know the percentage. I don't want to know if it's an A or a B. What the heck? Like, what's an A grade? Is this an A grade because it's 75%?
Yeah.
I don't know. I don't know what they consider A efficiency or B efficiency. Yeah. So, for engines and pumps and all of this, when you buy a 1,000 watt pump, you're not getting 1,000 watts of work done because some of it's going to be wasted. Okay. Let's see if I got another example, or is that it? Yeah, I have one more example, and I'm going to let you think about this. I'm going to let you try it before I do it. It's a hard one. It takes 30 seconds for a 1,495 kilogram car to reach its top speed of 214 kilometers an hour. What is the power rating? That's not how you spell rating, of the engine. Actually, this isn't that hard, is it? Okay. So let's have a look at this, and before I even started, I'll tell you that you all probably did it wrong. If anybody gets the same answer that I'm going to get, I'll be very happy. But I have a feeling that you probably all did it wrong. But that's okay, because I did that on purpose. Let's have a look. Here is the car, and it starts at rest, and then later it's going at a speed of 214 kilometers per hour. Let me just make that meters per second. 214,000 divided by 3600, and that is 59.44 meters per second. Yeah. So you might think, well, this is easy, because I know the time. The time is 30 seconds. And I know the mass. It's 1495 kilograms. So a lot of you probably did power equals a half mv squared over the 30. Or at least you were thinking of doing that, because it's similar to the earlier question. But I made a tiny change to this. I said that its top speed is 214. So when it's reached this speed here, the force here is going to equal the force here, because that's its top speed. In other words, there's a drag force here. Yep. So this actually makes a small little problem. It actually means the engine needs to be more powerful than what you might have just calculated, because it has to push against the air. It has to be a bit more powerful. So how much more powerful? Well, let's calculate it here. Let's just use Newton's law for a moment that says, and let me just forget about this for just one moment. Newton said F equals ma. Great, do we know the M? We do. Do we know the A? Yeah, we could know it. We don't know it now, but we could know it. It's going to be V minus U over T. Okay, so that's the A. So let's see what we get here. That is 2962 newtons. Great. So if I go back to my picture now, does that mean this is 2962 and this is 2962? No. What is this 2962? The total force. So the total is 2962. So this force minus the drag force has to equal 2962. So that force minus the drag force equals 2962. But what is the drag force? I mean, we have two unknowns. This is a big problem. Well, just to prevent maybe confusion, I won't call this F. I'll just call it T. And this total here, I'll call this F from Newton's second law. Okay, if I go back to this picture, this is a T. In the end picture, this must also be a T, because at the end it's balanced. At the beginning, this is a T, and at the end, what's this? Or sorry, at the start, what's this? 0, because it's only at the beginning. So the drag goes from 0 to T. So if we use an average, what should we use? T over 2, yeah. So this is T minus T over 2, which equals 2962. So T over 2 equals 2962. So T is twice this. That's the T. 5924 newtons. Now, why is that useful? Well, now we can get the power, because we can get the work. But I don't really want to use kinetic energy because of the problem I said earlier. So what's the other formula I could use for work? Force multiply the distance, yeah, over the time, which is 30. So that would be 5924 over 30 times the distance. What's the best formula to get the distance? U plus V over 2 times T. So that's 0 plus 59.44 over 2 times 30. Well, that's nice because they cancel. So I have that times that over 2. Now I don't know, maybe this is the same answer you got. No? Is it the same? Or is it a different answer? What answer did you get? What answer? Did anybody actually get an answer? Now, what did you get?
88K.
Yeah, that's what I was thinking. You should, if you did it the way I said would be wrong, you should get about half the right answer. And the reason you're getting about half the right answer is because the drag here is kind of like doubling the amount of force the engine would need to do. So if you did it the way I said, I think everybody did do it, then your answer should be, you should have gotten about half of this. Now this is a very hard example. In fact, I think it's too hard for the exam. But I just kind of wanted to show you that although the lesson seemed easy with the formulas, you can actually get very difficult ones here. It's not as obvious what the power might be, because then you have to think about drag and friction and all this other stuff here. So don't worry, I didn't expect anyone to get this. This is a hard example. And maybe even, I would say, too hard for the exam. But still good for you to see, good for your health. So if you can write this one down, please, and then I'll let you try the workbook. Too hard?
So this one will be in the exam.
It won't be in the exam. You see, they never make them this hard in the exam. The hardest one I've seen in the exam on this topic was my last example with the pump. The oil. That's the hardest one I've seen in the exam. But I like to make the examples in class a little bit harder than the exam. It's better for you. It'd be worse if I make them a little bit easier than the exam. Because then you'll think you're smarter than you are. And that's a big problem. I could not allow this.
Why drag is T over 2?
Yeah, the drag force is something that changes. In the beginning, it's 0. And then as the car goes faster, it gets bigger. Yeah, and at the beginning it's 0, and at the end it has to equal the engine force. Because it's not accelerating anymore. So if it starts at 0, and it finishes at T, then the average is T over 2. You see, the problem when the force changes is you can't use that in the formula. But the way we fix that is we can use the average. So if something is changing in the formula, we can just replace it with its average, and then we can use the formula. You know, these formulas that we use in physics, like a half mv squared, these only work if, you know, the values don't change. But what do you do if the mass changes? Well, what you could maybe do is just replace it with the average mass. You know? So one way in physics that we deal with problems of change is just to use the average value. That's why I use T over 2. Another way, if you want to think about this, if you can think about it this way, is if you did it the way I said not to do it, you could actually do it that way, but you need to say how efficient the engine is. And it might be difficult to see this at the beginning, but the engine is 50% efficient. If it has to defeat the wind and accelerate. But it's not obvious at the start that it should be 50%. It's only obvious at the end that it's 50% efficient in this story. It's a bit tricky, this one. Okay, continue. Yeah. Now, how hard did I make the ones in the workbook? Let me see. One to 5 should be okay for you. 6 and 7 are a bit hard. Try your best. You can start these for a few minutes. Here you go. Can I close this? Bruce, yeah?